Hey, good afternoon, everyone. Good afternoon. Can you hear me?
Good evening, Professor.
Hello? Oh, can you hear me? That's
Yes, I
weird.
can hear you. Good evening,
Oh,
Professor.
okay. Yeah. I couldn't hear myself back from my other computer. So I was wondering. Yeah. Sometimes if there's some system issue, then it would drive me nuts if I cannot fix it right away. But everything, all these, indicators. Uh, yeah, microphone indicator shows that it's working. So why is it not showing even? Okay, audio is working and the video is working. Why is not? Why isn't it? Right. Something's not right here. Hmm. Okay, give me a second. Let me get the things set up properly. Okay, there you go. All right. All right. Uh, all All right, so let me fix my. Oh, there. Okay, I guess I hear myself there. All right. Okay. So I believe everyone can see their midterm results and can also go over their results to review, right? That window is open only for 48 hours, right? You can see what you got wrong and what you got right. Only 48 during that 48-hour window. So after the due date. So please, uh, lose no time, waste no time, before it closes. Okay. All right. So we in our last class we stopped right here. The reason I was showing you this, actually, we were going to find return and you know mean return, uh, but the reason we stopped here, of course, we ran out of time. But the reason I was talking about the probability, and this is basically probability theory. I mean, you all understand weighted average is basically uh, every possible event, every possible event in our uh, dice example, um, every possible payoff weighted by their probability, right? Which is, in the case of fair dice, 1/6. The probability is all 1/6 because it's a fair cube. The probability cannot be different. And if you do that, it will be it will be the same thing as simple average. So the point I was trying to make the point that the simple average is a special case of weighted average that where all weights are equal, right? But if all weights are all different, then it cannot be simple average. However, the reason I'm talking about this is that when we calculate these returns,
Professor,
these
Professor, I don't know if
take
are you
into.
showing the screen right now? Because I can't see anything.
Oh, I'm sorry. I'm sorry. I was. Oh, I wasn't. I guess I wasn't. I should be sharing. Yeah, I'm sorry. Uh, yeah, thank you for reminding
Thank you.
me.
I thought it was just me. I restarted my thing and all that.
Yeah, I just went ahead, and forgot that I wasn't yet sharing my screen. Okay, so all right. So there you go. Yeah, we stopped in our last class. We stopped here, and you remember, right? This is uh, uh, basically illustration why um, a simple average is a special case of weighted average where all weights are equal, right? And then that is necessary. That was needed to explain that when we calculate monthly returns here, right? All those monthly returns are actually uh, uncorrelated with each other. In other words, uncorrelated events, especially short-term returns, are random events. Random. Random means they are not correlated with each other, right? Just because a particular month's return was extremely good, it doesn't necessarily mean the next month return will be extremely positive as well. I mean, day to day, even last week, last week the market was generally all down. I mean, uh, I don't remember if it was like that early last week, but daily returns early last week was good, but the market was generally from like Wednesday, market was going sideways. It wasn't particularly going up or going down, but relatively going down a little bit, right? Like mild, moderate, negative returns since like midweek, right? Last week. And then Friday ended. Friday's market ended with negative return. But generally the market was going sideways last week, and the market regained today, but it, we don't know. It might still be uh, testing the water. It may be still going sideways a couple of days, but usually when this happens, it's basically you have to watch the volume, price movements, price actions, for example, price actions. I got a lot of in my portfolio. I got like 16, 18 stocks that have all gained, like total change. However, I also have about uh, 8 stocks that are showing negative. But even day to day today, some of them gained, most of them lost, and also in this positive range, most of them gained, some of them lost. But when you see something like this, you have to also. This is something I'm digressing. Um, but if the volume, I mean, think about it. If the trading is not very frequent, right? Trading happens, but very infrequently during the day. Even a small volume can change the price. I mean, the trade certain stock is very quiet, no action, but even a sale of um 10 shares. Of course, 10 shares cannot be traded uh, because trading happens by lots, and one lot is 100 shares. Uh, but even if you have only 10 shares, it can still happen because the brokers can pull those small orders together, small sell or buy orders together, and uh, they can make a lot. They can make one lot, right? For example, if I'm selling, 10 shares, they can pull together the sell orders of 10, 20, 30, uh, uh, multiple odd lots. Any order that is under 100 shares is called odd lots. Odd. They can pull together odd lots and make a transaction. However, so I don't want to digress a lot. Usually, when the market goes sideways and generally, showing a small, a downtrend, that's generally, and that means trading volume is small. Um, that is an indication that indicates that um, individuals, weak individuals, are selling, and big institutions are not selling. They are holding on, and they are trying to shake off the weak individuals. Think about it. If weak individuals are selling, they fear, they are in a panic. Oh well, there's a lot of negative news. Maybe I should sell now. If they sell, even small volume trading can, of course, lower the price. So if that happens, they sell the shares, they sell the stock, uh, and they are shaken off. And because they sold the stocks, the price would go down. And then the big institutions who are not selling, who are holding on, right? Uh, so in other words, you must have grits, right? The grits with fundamentals. If you have this firm understanding of and conviction in the positive fundamentals of the company, you won't sell. Um, Even if there's a slight negative price action, you don't sell. And individuals are easily swayed, and they sell because they are weak-hearted. They don't have grits. But institutions, they don't sell. They have grits. Um, and they shake off these weak individuals. Prices are lower, then they snap it up, right? Think about it. They snap up these shares that are sold, and they snap it up at lower price. So anyway, I don't want to digress too much, but the point is, day-to-day movements are quite random. They're not correlated. So, and this is month to month, still quite random. So, simple average, okay? Simple average is the right average that we need. But uh, to bring us to that conclusion, right? This illustration was used. So let's continue to listen, right? And after we finish up, then we're going to go back to this uh, Apple data that we downloaded last time. Okay. All right. So let's take a listen. Average, right? So it's a special case of weighted average. Simple average is a special case of weighted average where all the weights, right? All the weights are the same, right? Okay. So then then this comes to, if you do this, this will come to $3, $3.5, $3.50. Okay, $3.50. Actually, think about it. There are three pairs of 7 times 3, 21. 21 divided by 6, right? You'll get, right? So think about it. This is exactly simple average, but this is the expected payoff. Expected payoff. In other words, because it is, all rationally expected. Why? Because you factor in the probabilities of each event, each number that can come up, right? So this is the most rationally expected, which is just the average, right? In this case. But if the weights are different, it will be weighted average. But with the same weights, it's just simple average, right? But then now let's think about it. Can you win $3.5 in this dice game? Is it possible? No, it's not. You can't win 3.5. Why? Because 3.5, that number doesn't exist on the dice, right? Right? But still, even though it's impossible to win $3.5, but that's the most rationally expected value, right? So this is why average is called expected, right, or expected return. In this case, let me go back to, okay, application, go back to Excel, okay. So now this is why it's called expected return, right? Expected return is the mean return. So what this is telling you is, on average, right, over the last 60 months, Apple earned 1.81% return monthly, right? So 1.81% seem very much, but suppose Apple grows. This is the growth rate of Apple. So then, starting from, let's just try this simply, right? If we compound this price, right? If we compound this price, like April 2015 price, right? 1 plus this, right? Think about it. Annually, it's going to be the annual return will be 1 plus this raised to 12. That would be annual, right? Isn't that right? And then over 60 months, right? If you compound it 3 to 60, right? This is what we would expect, 60 months later. Of course, it may not be, because we are, about $50, right? Short of this expectation, right? But still, think about it. The idea is, if there was not, a lot of fluctuations during, these last 5 years, right? If it was just smoothly growing at this, we would have got to 388 by now. And if you, another thing, what would be the annual return then? Of course, you raise this to 12 and minus 1. Annually, if it grows at 1.81%, annual is going to be, right, 24%. Make sense? Okay. All right. Next thing. Next. So you would be interested in, we can copy that, and I'll take it here and paste. But I'm going to paste only, pasting would, if you paste it in, of course, it's going to also bring in all the formulas, right? Because these are based on the formula. And of course, we're going to be losing that because, we don't have the data. But what I would like to do is place it there, and instead of paste the formula, we'll just copy the value only, the numbers, right? So if you go to a paste special and paste values, right? Now let's see. You see, only the values are copied, right? I'm gonna close this, right? Then there's one thing you can do. Don't you want to know what was the best, highest return during this period and lowest return? Don't you want to sort it in like descending order? Then yeah, I did that, and then it was sorted in descending order. So the best month for Apple was August of 2018. Just in 1 month, they gained almost 20%, right? And then the worst month was November of 2018. In just 1 month, they lost almost 20%, right? It may look symmetrical, but no, it's not really. Why? Because if it looks like if it is 19% on the right tail and 19% to the left tail, and if the mean is 0, then it's cyclical. The mean is not 0. Mean is 2, right? Mean is 2, and then upper tail ends at 19% or 20%, 19, yeah, almost 20%. Lower tail, the left tail ends at 18%. So it's, yeah, you can say it's symmetrical in the sense that mean is about 2, and to the right it is 20%, to the left it is 18%. So it's almost symmetrical, but it doesn't, it's just a coincidence, okay? Next thing, now think about it. Wouldn't you want to know, and now that you know the mean is 18%, next, don't you want to know the average deviation from the mean, or average fluctuation from the mean, right? Don't you want to know every month they fluctuated, the return fluctuated, right? From the mean, right? So if you knew the average fluctuation or deviation from the mean, don't you think it would be the next logically that's what you want to know next, and then at least you would have some rough idea about how wild the swing is, right? Yes, then to do that, we would like to, what would you do then? Of course, I will take the difference. I mean, what's the idea? The deviation is basically, we want to know the average deviation from the mean. So deviation is basically the difference between each monthly return and the average, isn't that right? So what I'm going to do is I'm going to take the difference between each monthly return and the mean, okay? So that's, but then I'm not going to do this one by one. I will just copy and paste it all. I'm going to just copy and paste it all the way down. But then you copy and paste it. You have to also realize that as D2 goes down to D3, this will go down to D64, and there's nothing in D64. D63 is the average, so you want to keep it locked into D64. So when you hit F4, and then the average will be locked, right? D63 will be locked. So when you drag it down, right, it's not going to change, right? It will be always, okay. So then, next question is, I want to then, good, I'm going to sum everything, right? So you want to take average, you will first need to sum everything, right? Isn't it right? And then divide it by the number of data points, right? So you're going to sum everything. And you want to divide it. Then when you sum everything, what happened? It's 0. Why is it 0? I mean, did I do something wrong? No, you didn't do anything wrong. You summed everything. But why is it 0? It's supposed to be 0. It's bound to be 0. Why? Why? Remember what we did was this column, right? Column E. Column E is the column of what? The deviations from the mean, difference terms. Excuse me. What that means is mean is a neutral number. Mean is a very neutral number. And so if you take the difference with the mean, that means half of these data points are positive, and half of the other. So if you sum everything, they will cancel out, right? The positive numbers will cancel out with the negative numbers. So it's bound to be 0. Then you are at a loss. You don't know what to do. I mean, how do I then take the average deviation if the sum of all these are, sum of all these deviations is 0? I mean, dividing this by 60 will do nothing. We'll just give you 0. So it looks like you are at a blind dead end. No, actually, you're not at a dead end. You can get around this. So question is that how do we get around this problem? Some of you may say, so what if we use only positive difference term? Well, going to happen if you use only positive terms? It's not going to give you a correct picture, correct representation of the deviations, right? In other words, you're losing the actual dynamics of the price or the returns, returns trend. So you cannot use, only the positive numbers. Then there is one solution. One solution is you will square the difference terms. Think about it. Squaring the difference terms, if you square the difference terms, everything will be positive, right? Any number squared is always positive, isn't it right? So we'll retain all the 60 data points. We're not going to lose any of them. And then we can find the average of all these, right? Think about it. Difference, when we say difference, right? Deviation, right? Some are negative, but negative means it's just to the left side of the left-hand side of the mean. Make sense? The negative values are the distances to the left of the mean, right? And the positive deviations are the numbers that are to the right side of the mean, right-hand side of the average. So actually, in terms of the distance, there's no negative distance, right? It's just to the left of the mean or to the right of the mean. So there's no, it's perfectly okay to use, square terms. And all you need to do is then simply simply square it, right? So we got that, and I'm going to give it, I'm going to do, where's speakers? Okay, and I'm going to also give it percentage, right? That's what to be consistent, right? And then don't leave it like this because there's a big difference, right? So always use 2 decimal places, right? Or 3, list 3, right? 2 is fine. Now you can drag it down. Okay, then you auto sum everything, right? Okay, so this is, let me do this. Not only this, I will highlight the entire cell. Make it 14. Okay, what is this? This is the sum of all the squared difference terms, right? This is the sum of all the squared difference terms. So it's got a name. It's called SSQ. Okay. So some of you may ask, so Professor, what is SSQ? What's SSQ? SSQ sounds very cool, doesn't it? It's like a special task force, special squadron, right? It's a cool name, right? But what do you think is SSQ? What did we do? What is this? This is the result of squaring all the difference terms, right? So what does this mean? This is squared sum of squares, sum of all the squared terms, right? Squared difference terms. So SSQ, okay? Yeah, it's the dark, so let me make it like lighter. Okay. So what is the next thing to do then? Since this is the sum of all the deviations, right? We want to divide it by the number of data point, right? So I'm gonna, because we want to find the average deviation, I'm gonna divide it by, and we know we have 60 data points because, but then just to make sure, I'm not gonna enter 60 there. Instead, I'm gonna have Excel. I'm gonna make Excel automatically count, right? So I'm gonna use count command, and I will count all the data, right? Okay. So then it's 60. Automatically, it's going to give you 60. But then, oh, you might think, okay, that's good. We got that. No, not yet. Why? One thing you have forgotten is that this has a statistical quality, statistical characteristics called, a loss of 1 degree of freedom. Loss of 1 degree freedom. Okay. So I'm going to come back to this loss. Explain. I'm going to come back to this later. Loss of 1 degree of freedom. But no, for now, take my word for it. You cannot divide it by n. You will have to divide it by n minus 1 because because of loss of 1 degree of freedom, right, in the data set. So if you do that, okay, and that's, it's just too long. You don't want to. I'll just, use only decreased decimal and use only like 3, right? Or 4 at most, right? 3 is enough. And make it bold. So then, are you saying average deviation is only average deviation per month is average deviation a month is like 0.618%? Only decimal? No, I'm not satisfied. This is called variance. Okay, this is called variance. What is variance? It's the average deviation, right, of every monthly return, each monthly return, deviation of each monthly return from the mean. But then this is actually a blown up picture. It's not the life size picture, right? Isn't that right? Why? It's a blown up picture. Why is it a blown up? Because we blew it up. We blew up the difference, right? Actual difference. We blew it up by squaring it. We squared it, right? So this is not the life size picture of the average deviation from the mean, but this is actually a blown up picture. So, but then we know how to turn it back to life size picture. You know why? Because we blew it up by squaring. So then we know how to turn it back to life size, right? How do we do that? How do we do that? I just dragged it down because of the formatting, right? Because of the formatting. Because we know how to revert it back to a life size picture because we blew it up by squaring. So to turn it back to life size picture, you will only need to take the square root, right? If you take the square root of it, then it will be reverted back to life size picture. So all I need to do is, how do you take the square root of that? Either S or T, that's the square root command, or you raise it to half power. You raise it to half. Remember, square root is something raised to x raised to half power, right? So if you take the square root, okay, that's what it is. And if you take the, if you adjust the, okay, let me adjust. If you adjust the decimal places, 7.86. And so that is the life size picture of the average deviation from the mean. And it's got a name. It's called standard deviation. So standard deviation is, okay, what's standard deviation? Is the square root of variance. What's variance? Is the squared standard deviation. So variance and standard deviation are like twin brothers, right? Twins, right? A big twin, a little twin, right? Dr. Evil, mini-me, right? But this is the life size picture. Okay, so we got to the standard deviation, and what does it mean to us? There are at least 3 things that this can help us. One is, of course, this is average. Standard deviation means this is an average deviation, right, from the mean, right? And it's the life size picture. And you might wonder, also some people may ask, if variance is the squared term of standard deviation, and if the standard deviation is the square root of variance, how come standard deviation is bigger than the variance? Shouldn't variance be, because it's a blown up thing, shouldn't variance be? No. This is because we are dealing with a number that is less than 1. Think about it. If you square 2, then it becomes 4. Any number squared, any number greater than 1 squared will become greater than itself, right? But then number between 0 and 1, when you square it, what does it become? Think about it. 10%, 0.1. If you square it, what does it become? It becomes 0.01. Isn't that right? 0.5 squared, what does it become? 0.025. Right? Makes sense? So any number between 0 and 1, when squared, it's smaller. It becomes smaller and smaller and smaller. Right? So there's nothing wrong with this. Right? Makes sense? All righty. So that's it for today. I want you to replicate the work, as we do this. I mean, you have downloaded this file last time, so
well, we will do that. we will actually, replicate this work, right? As we close this. Now, I want you to open this file. We worked on this file last week, and you must have it on your computer. So please open it. And if you don't have it, I don't know what else. Maybe I can. So how many of you don't have it? If you worked on this last Thursday, you must have it on your computer.
But if you don't, I just want to know how many. Everyone has this file. Let me know, please. Anyone does? Please raise your hand if you don't have this file. I don't see any hands, so I would assume.
I have it.
Okay, good, good. So I would assume everyone has this file. Great. All right, Zainab. Great. And since nobody raised hand, I would have to assume that everyone has this file. So I'm not going to post this file again because, and I have, there's a, okay, if you go back in the, this topic 5 folder, there's a file from back, 2020. So obviously it's not going to be the same data, right? So ignore this. Anyway, after today, I'm gonna post. I'm gonna post again the updated work. Anyway, so if you have this now, it's time to find return. Okay, so the return. So of course, this is not. This is not August for. This is not August 1st data, right? This is not August 1st price. I told you this is just the way it is. The date is represented. And since we downloaded monthly data, so this is the end of a closing price at the end of July. And since August hasn't ended yet, this is the this is the closing price as of end of last Thursday, right? So it's not full August. We don't have full month data, but it doesn't matter. I mean, anyway, end of August, it will still be a random number, so it won't make it that much difference. So we all know. Oh no, this is not the. I'm using the wrong keyboard again. So return is, we all understand that the return is. Okay, let me. Right, we all know. Return at time t, one period, right, is pt minus 1 over pt minus 1. Okay. So it's not difficult to understand. All right, we're gonna simply, this is pt, and then this is pt minus 1. And something not that difficult to understand. But years ago, when before the pandemic, when the MCC had mostly only traditional students who just graduated from public high schools, in New York City, New York City public education system. There were some students that could never understand what PT minus 1 is.
right? If this is PT, then obviously this is PT minus 1. But it was so difficult to convince them or make them understand. Uh, I hope, I'm glad, since the pandemic, more sensible people with no time or space restriction, more sensible people, taking classes. So now we get not, so. And if you give, so this is the return between end of August and the most recent date in August, end of July and most recent date, last Thursday of August. And we're going to give it percentage, right? Always the return is expressed as percentage, but don't leave it like this. Give it 2 to 3 decimal places, 2 to 3 decimal places. And once you're done with that, you just drag it down. But only up to this, right? All right. Actually, we have how many data points here? Return, as for return, 61. That means, price data, we have 62. Of course, because we can have only 61 returns data when we have 62 price data points, and we need only 60 because 5 years is 60 months. So we're going to cut it off here, right? We're going to cut it off below this when we actually, but for now, what are we interested in? We want to know although returns have fluctuated like this, we want to know what was the average or the mean return, right? So what we're going to do is, of course, take the average, right? I'm going to take the average of, so we're going to take the simple average, right? Something average, in parentheses. And we're going to put these 60 data points. You're not gonna include this because that's 61st data point. Okay, then in the small squares, you see this box to the right? It says 60 R times 1 C. What does that mean? 60 rows times 1 column, right? So that confirms that I have 60 data points. You don't have to close. Once you hit enter, it will automatically close the parentheses. Hit enter. Okay, so this is the, I'm gonna bold it and highlight it with, and then this is, as you know, this is the average or average return or mean return. Okay. Okay. Now, if you want to check when was the best month and when was the worst month, right? for the last 5 years. During the last 5 years, all you need to do is just select, click here, and the entire worksheet is selected, right? And then copy and open another worksheet and go to home, paste. But this time I want to use paste only values, paste values only. And there's a reason why. If you do that, now only you see only the numbers are pasted, not the formula. And the reason I wanted to do it this way is I want to sort this in descending order, right? From the highest to the lowest. And as I do that, then these places will change. If the places change, then it's not going to be the same number anymore. Returns won't be the same anymore. It's going to be totally, chaotic. So it's better to remove the formula and just work with the numerical data. Now I can sort this. Go home. Sort. Largest to smallest. Okay. Wow. Wasn't 2020? I mean, the pandemic started, right? We went into lockdown actually from around March or April of 2020. But August of 2020 was the best month. And that makes sense because after lockdown, the demand for computers went up. Isn't it right? Demand for computers went up. So no wonder. Well, when was the worst? Come on. Let me redo this because this was also in a contiguous range, so it was also included. However, I will give it. I will put a gap so that this data won't be contiguous. Okay, then go back and largest to smallest. Yeah, August 2020 was the best month. The worst month, November 2018. And I think in my in the video, because think about it, the video, as I said, the video was made in 2020. 2018 was included in the 5-year data range. Isn't that right? And also November in the video, November 2018, sometime 2018 was the worst month. Yeah. And it was at the time, it was also negative 18, right? In the video, it was also negative 18.4 something, right? So that was the worst month. This was the best month. Now, so we're going to, once you have verified that, we want to come back to this. Okay. If you're back here, now we want to know what was the average deviation. What was the average deviation from the mean in the returns data, monthly returns, right? So to find the average deviation, right? Deviation is the simply difference, isn't it right? Deviation is the difference. Difference between this monthly data, monthly return and the mean return, right? So we're going to take the difference, right? This minus this. And since C60, this shouldn't change, right? This shouldn't change. This should not change as I drag it down, right? I'm going to drag it down. But, if I drag it down without locking this, it's going to change as we move on. So I'm going to hit F4 and lock it. And then I'll drag it down. So these are difference terms, right? These are differences. So you want to, let's say you want to find average of this. There are two ways. Of course, you can use average command. All you need to do is you can drag it to the right. Average of all this, of course, it will be 0, right? Another thing is you can sum everything. Sum everything there. And you will see this is 0. Right? Sum is already 0. And if the sum is 0, average will be 0. And I explained in the video, it's bound to be. It's bound to be 0. Why? Because almost half of these are, mean is a number that is based on, mean is a very neutral number. So it was produced, mean was generated by half of the data set that are positive numbers and half of the data set that are negative numbers. Difference terms are basically, difference terms are basically based on the difference between individual returns and the mean return. And then therefore, half of them will be positive, half of them will be negative. Not exactly half, but almost, right? So it's bound to be 0. Mean is bound to be 0. So we need to get around this problem. And how do we do that? Well, we can square all of these difference terms, right? And anything squared is always positive, right? Even the negative terms squared, positive, right? So we'll just simply square column B, right? And then, of course, I'm going to give it percentage and give it like 2 to 3 decimal places. And you drag it down. Okay? And then we're going to sum all of this. Okay? Now, since I don't need that meaningless sum, I'm gonna just move the label to the right and just recycle that label. Okay. Okay. And then change the highlight, we'll change the color. And usually, it's best not to use too dark color because the font, if the background is too dark, the label is not visible.
And if you print it out, even on color printer, uh, not to mention the black and white printer, if you print it out, it's totally invisible. So always use light background. Now this sum, this is sum of all the squared terms, hence it's called, that's cube, sum of squares, right? So you want to, okay, what do we want to do? We want to find the average deviation from the mean. So these are the deviations from the mean. So we want to find the average of that. So what I want to do is I just copied it over just for the background color and the bold font. So all you need to do is simply just divide it by number of data points, right? We have 60 data points. But you might want to just jump in and just type in 60. But I've been telling you not to do that. I've been telling you not to do that. Because if by any chance you make a mistake, then obviously that won't be reliable, right? The estimates won't be reliable if you and you cannot reapply it. When you hard code anything, you cannot reapply it, right? Reusability, reapplicability is a very useful feature and very critically uh, essentially useful feature in Excel of using Excel modeling or any computer programming, right? Reusability is basically efficiency. If you have to write programs, all over again for every uh, command or every every command that you have you want to run, that would be a very stupid thing because but you don't want to do that again. I mean, building a algorithm is basically based on reusability, right? If you can reuse the same algorithm over and over, you can simply replicate it. So here, so hard coding is not a good thing. Soft coding is always recommended. So you will count. You will use count command. Okay, so you might think, oh, that will take care of the problem. No, once again, no. You need to subtract 1, and it's because of the statistical properties called loss of 1 degree of freedom, and it will be explained again in the next video. So subtract 1, hit enter, and this is okay. So this is the average deviation from the mean. However, this is called variance, and it's not the life size chart, right? It's not the life size picture. Why? Because it was squared. All these deviations were squared. So actual life size picture should be, when you compress something, you can bring it back to original size by decompressing it. When you blow up the picture, you can take it back to life size picture by the reverse process of blowing up. And blowing up here is squaring. So taking it back to life size picture is by taking the square root, right? So this one, once again, I just dragged it down uh, to copy the font and the formatting, the background color. So basically, you will need to take the square root, right, of this. There you go. That's called standard deviation. Literally, standard is standardized. That means it's an average, right? Standard deviation. Again, you can find this by taking the square root is what? Half power. So you can raise it to half power, and you get the same result. Okay? Same result, right? So everyone got the same result? Please confirm. Everyone got the same result? No one? Any any questions? Okay, good. Zainab, you got it. All right, good. What about the other people? Did you all get the same result?
Yes, yes.
Okay, very good, Brandon. Very good. All right, I will assume the rest of the class got the same result. Okay, so please save this file. Don't throw it away. Save this file. Okay, so now we're gonna continue with the next video, right? It's already 7:04. So I guess this is a good time to take a 10-minute break. So let's take a 10-minute break and reconvene at 7:15. Okay, reconvene at 7:15. All righty. So take a 10-minute.
All right, we're back. We're back. So let's go to the next video. Okay, take a listen.
Risk and return that that we were discussed, in the last class. And in our last class, we calculated basically expected return and the variance and standard deviation with the data downloaded for Apple. Now, so if you remember the data that we downloaded, right? And of course, we downloaded monthly data, but specifically, if you looked at the daily data, daily price data, you would see daily price data is almost like a random occurrence, right? I mean, in the long run, there is a deterministic trend in the long run, and over the past 5 years, and certainly over the last 40 years, Apple has been consistently growing, right? So there is a positive trend, which is a deterministic trend, right? Positive deterministic trend. But looking at the daily data from day to day, also intraday, if you look at the intraday data, by every minute, by every 5 minutes, or by every minute, the fluctuation is so random, right? Of course, within the day, the price action is a movement between, the high of the day and the low of the day, but that movement by itself is very random, right? And then just because today price was, today's price was higher than yesterday's price, it doesn't guarantee that tomorrow's price would be higher than today. Also, even monthly price, generally, if there's an in the long run, I mean, we got Apple's mean return, right? And Apple's mean return was almost like 1.81% or something like that, which means on average, Apple is growing at monthly at average growth rate of about 1.81%, right? So clearly, on average, there's a positive growth monthly, but in reality, actually, month to month, it could be negative, right? So 1 month it was positive return, but the next month it can easily be a negative return, right? So in other words, actual individual data, actual individual data points are basically random variables, right? Random variables. That's why we needed to, we wanted to find the mean of this random variable, which is, mean of the return, right? And then standard deviation of the return. So we talked about this, mean is the expected value, right? And this is a notation you should recognize. What is this? This means X bar. If the mean of X, right? X is the random variable, like, the numbers on the a dice, right? When you roll a dice, I use this example. Any number, randomly, any random number can come up between 1 and 6, right? So this bar means mean, average, right? And then a sum of all the individual numbers, right? Times the probability of the number coming up, right? So xi, where xi is the number. So in the whiteboard, I basically wrote this. It's the same idea. So I run from 1 through n, right? But again, if you think about it, in this case, n runs only up to 6, right? 1 through 6, and probability of if I is 1, X would be $1. If I is 2, X would be $2, and so on, right? Now, probability of each number coming up, right? Each I, probability of xi, is all the same, 1 over 6. So I told you, in case of this dice game, because dice is a fair cube, and the probabilities are all the same. So eventually, although we represent it with the probability, but since the probability is all 1 over 6, you factor out the common factor, and then it simply becomes the simple average, right? So I told you when probabilities are all the same, the average of all those possible events, or average of those possible events, is the simple average, and simple average is a special case weighted average where all the probabilities are the same. So 1 over 6 in this case, all the probabilities are the same, right? 1 over 6 in this case, and of course the sum of all the probabilities must be 1, right? If you add sum all the probabilities, it must be equal to 1. So this is where you can express the mean. And so, of course, probability probabilities are probabilities can be described by a histogram like this, and it's called and the possible events are discrete. Discrete. For example, if you're rolling a dice just once, the possible occurrences are 1, 2, 3, 4, 5, and 6. So we will have probabilities, and it's called uniform probability distribution, uniform distribution, because each number has the same probability. But this is an example of probabilities of flipping a coin. Now, if you flip the coin 4 times, right? If you flip the coin 4 times, first of all, there are 2 probabilities, 50-50 of either head or tail, right? And then there can be 4 possible. And if you flip it 4 times, right? 4 flips, right? Then there could be a. I mean, if you flip it two times first, let's think about 2 flips. There can be head, right? There can be head, tail, right? Or there can be a tail, right? And there can be a tail and head, right? So that's a example of 2 flips. If you do 4 flips, the probabilities will be and there will be a 2 to the 4th. 2 to the 4th is 16, right? 16 possible outcomes, right? So head, 4 straight heads, right? Or head, 3 heads and 1 tail, 2 heads and 2 tails, 1 head and 3 tails, right? And then 4 tails and 0 head. I mean, that will be 16. But actually, these are actually although it says 4 flips, but it looks more like 2 flips, right? 2 flips, because then there will be 4 heads, 0 heads, right? And this is 1 head, 3 tails, 2 heads, 2 tails, and so on. But if you do these, experiments, you will see the distribution would look pretty much like this. But still, if you connect those top of those histograms, it would look like a normal distribution curve. But it's not a curve just yet, because the possible events are still discrete, right? If the possible events are continuous, right? Then it will be a perfect curve. And by continuous, I mean, how would you get a continuous distribution? You remember Euler's number, right? If you use Euler's number, in other words, exponential function, then it can emulate the continuous distribution. But anyway, so that was discrete distribution, but this is continuous distribution, and this distribution curve is called normal distribution curve, and this looks like a distribution of height, right? 5'8" being the mean, and 6'6". This is not the end of the tail. This looks more like 2 standard deviation from the mean. 4'10", also 2 standard deviation below the mean. Now, so 5'8", 6'6". There's almost about 6 inches and 10 inches difference, right? 5'8", so 12 inches. 5'12" is 6, right? So 4 inches more, right? There's 4 inches to 6 feet and 6 more inches. So 10 inches is 2 standard deviations. So it looks like 5 inches is 1 standard deviation. So what does this mean? So if you roughly, if 1 standard deviation is 5 inches, right? People who are so 5 inches above this is like 6'1", right? So 1 standard deviation above mean is 6'1". 2 standard deviations above mean is 6'6", and 1 standard deviation below mean is 5'3", and then 2 standard deviations below mean is 5'10". So this would require some understanding of normal distribution properties. Now, a lot of things in nature are normally distributed. Height is one good example. Okay, so suppose we have, let's see if I can use, yeah. So
if 5'5", that's not 5. That looks like 6. Oh, it has to be one line. If 5'5" is the mean, right? Maybe I can use the pen. Oh no, that's signature now. Okay. So this was like 6 foot, and this was like 5 foot, 5'3", 5'8" is the mean, right? So within one standard deviations, right? There are 68%. There's a 68% probability. 68% probability that out of 100, right? If we have like 100 observations, in other words, if we measure the heights of people, and if we randomly pick 100 people, and if we measure the height, and if the average height is 5'8", about 68%. The better way of correct way of saying that is the probability of anyone randomly picked is the probability of anyone randomly picked falls between 6'1" and 5'8", right? Is 68%. You understand? So out of 100 people, right? So we have the average height is 5'8". So you just randomly pick 100 people passing by, and if you pick one person, and the probability of that person falling into this range of 5'3" and 6'1" is 68%, right? So the probability of falling within one standard deviation around the mean is 68%. That's what it means. And then that means the probability of falling within falling between the mean and one standard deviation above mean is half of that, 34%. And the probability of falling between mean and one standard deviation below the mean is another 34%. So the sum of those two is 68%. If you are like 5'11", right, you are one of those people who fall into this 34% probability, right? If you are 5'5", you're also in this 34% probability, right? Now, and then there is then the probability of falling within two standard deviations around the mean, right? Two standard deviations around the mean, right? This is two standard deviations, right? It's 96%, right? The probability is 96%. 96%, right? So if you pick anybody out of 100, right? It doesn't have to be 100, but just to make it simple. I mean, if this is if this height statistics is from a large population, right? From a very large population, let's say you measured everyone's height data of everyone in the U.S. That's almost 300 million people, and the average height. And of course, you will have to measure the height of the grown-ups, right? Grown-ups. Obviously, but a 2-year-old baby or 1-year-old baby will not. I mean, if we include still, even if you include the entire population, I mean, if this 5'8" is the average of the entire population, it will still hold, right? But anyway, the idea is 96% of the population, right? The population here in this context doesn't mean the population of people. When we say population, it means entire data set. Okay, entire data set. So in other words, if you measure the heights of everyone in the U.S., in other words, 300 million people, right? That's the population. But you cannot do that. I mean, realistically, that is, impractical, right? You have to track everyone down and measure the height. That's impossible. I mean, it may not be impossible, but too time-consuming and impractical. So you just use a sample group. So you pick like 1,000 people in within 5 boroughs of New York City. Okay, because 1,000 people is a smaller sample than the entire population, right? That sample group is that sample group provides a limited data set, but that if that data set, that small sample group is randomly picked, right? Then that random sample uh, uh, random sample can represent the entire population. But once again, if you just pick the random sample from New York, 5 boroughs, greater New York area, that cannot be a sample for the entire U.S. I mean, to pick, 1,000 people, a random sample of 1,000 people, then you have to go around the entire 50 states and then pick, randomly 1,000 people out of 50 states, right? And in equal proportion, right? So to make 1,000 people from 50 states, from each state, just 20 people, right? Randomly picked. Again, so that's the distinction between population and sample, right? Population is the entire data set. Sample is a local data set, limited data set. Okay, makes sense. So let's say, so this notation, you see this notation mu, that's Greek character mu, right? What does that mean? That Greek character mu, that's for Roman alphabet M, so that means mean, right? The average, right? And this is Greek character sigma. And of course, sigma is S. That means that stands for standard deviation. So basically, if you pick, I mean, if this is, let's say even, sample data from, 5 a greater New York area, right? 5 boroughs plus, surrounding counties. And the average height is, 5'8", right? One standard deviation is 5 inches, right? And 2 standard deviation, 10, right? And so on. So that means if you randomly pick anybody, right? If you go down to the 42nd Street, Broadway and 42nd, randomly pick anybody, the probability of that person falling within 1 standard deviation around the mean, right, is 68%, and the probability of that person falling within 2 standard deviations around the mean, which means, so this would be 5'2", this would be 6'6", right? So the probability of a random person falling, and that's a quite broad range, 5'2" through 6'6". That's a very broad range. Wouldn't that have a high probability? 96%, right? Anybody pick randomly, right, falling in the height range, that's very high, 96%. Right? That means the probability of the person falling between 6'1" and 6'6", right, is 13%. Right, it says 13.6, but roughly, that's rounded. Why? So this is 96%, right? 2 standard deviation is 96%. The probability of falling within 1 standard deviation around the mean is 68%. The difference is 28%, isn't it right? So half of that, 14%, falls here. The other 14% falls here. Makes sense? Okay. So if the probability of falling within 2 standard deviations around the mean, 96%, then the rest of it will be 4%. Makes sense? The rest of it will be 4%. Out of those 4%, 2% will fall here in the upper tail area, and 2% will fall here in the lower tail area. So that 2% means what? I mean, think about it. That's a very rare, low probability, isn't it right? Either way, right? So what is the probability of randomly running into a person who is taller than 6'6"? Huh? I mean, if you walk down the street and randomly run 100 people, what is the probability of running into someone taller than 6'6"? Exactly, that's less than 2%, isn't it right? And also, if you just walk down the street and randomly run into 100 people, what is the probability of running taller than 5'2"? That is also like 2%, right? So both tails, up tail, lower tail, right tail or right or left tail, these tail areas are called outliers, right? Outlier is literally lying outside the normal distribution, 96% range, right? Extremely high, extremely low. I mean, they both have low probabilities, extremely low probabilities, but the upper tail, lower tail end, right? Upper tail end, lower tail end. Okay, so that's why it's called outlier. They are lying outside. Now, then how does that? What does it have to do with Apple's return? Now think about it. So Apple's mean was like 1.81%. Let's just say 2%, right? 2% for simplicity's sake. And Apple's standard deviation was what? It was about 7%. right? It was greater than 7%. For simplicity's sake, let's call it 7%. So if the one standard deviation is 7%, right? One standard deviation above mean is 9%. Two standard deviations above mean will be this plus 7, so like 16%, right? This point will be 60%, this point will be 9%, right? And then one standard deviation below mean will be negative 5%. Negative 5. And then two standard deviations below mean will be negative 12%, right? So this gives us a better idea about what our chances, what is our probability of earning our target return. For example, Apple's mean return is about 2%, right? Monthly, right? That means you have 34% probability of earning anywhere between 2 and 9%. You also have 14% probability of earning anywhere between 9 and 16%, right? Remember the best month was like August of 2018, right? And if you go back to the data, you will see. And at the time, they earned like 19 point something percent. So that was 19 point something is really, really this upper tail outlier. That was an event that has only about 2% probability of happening. But that happened in August of 2018. Also, it also means you have 34% probability of earning anywhere between 2 and negative 5% return, right? Next month, right? And also that means you have 14% probability of earning anywhere between negative 5 to negative 12% return. And you also have 2% probability of earning anywhere below negative 12% return, right? And also you remember the worst month for Apple was November 2018, and they had like negative 18% return in November. So that lower tail 2% event happened in November 2018. Outliers can happen, but with 2% probability. Make sense? Now, so with that, okay, let me go back there already. I guess this is causing a lot of flickering. So let me delete this because it's causing. Alrighty, so then going back to so this is basically what variance is, right? How we found variance as standard deviation already yesterday, but this may look a little unfamiliar. But let me show you. Let me stop this and go to a whiteboard. Okay, I'm gonna. So what is variance? You remember what we did in the last class, right? Variance of x. X is the random variable, right? But look, for our example, with our example, x was r, the return, monthly return. Remember that? I'll just call it x for now because our return is a random variable, and we just call random variable x. Okay. So well, how did we find the variance? First, what we did was we found sum of squares. Right? Remember what sum of squares? Sum of squared difference terms, right? And then we divided it by n minus 1. So what were the sum of squares? Sum of squares were literally sum of all the squared difference terms, right? xi minus x bar squared, right? Remember this? What was this? This was the difference between each monthly return and the average return, right? Isn't it right? We did this and we squared it. We had like 60 of them, and then we summed everything, right? So number I ran from 1 through 60, right? And then we did n minus 1, right? Of course, if we write it in general notation, it would be I equals 1, meaning I runs from 1 through n. But in our example, n was 60, right? So we found variance this way. And then we took the square root of variance, right? To do what? We took the square root of variance to find the standard deviation of x, right? to find standard deviation of x. This is horrible. It's not handwriting. Please don't. It is mouse writing. It's with the mouse that I'm doing this. So it's more like a drawing. It's very difficult. So we know. Then all we need to do is we, simply. Xi minus x bar raised to squared, right? Over n minus 1. So this is our formula for variance and standard deviation. But then, what you saw on the slide was a little bit different. Why? What you saw on the slide is with the probabilities. In other words, in our example, every monthly return data point had the same probability, right? Those were like, the probabilities were 1 over 60. They all had the same probability. So we, even if we use weighted average, it's still the same thing as the simple average, right? But if the probabilities are different, that's how you do it. You multiply everything by its own probability. And the notation in the slide is that case, just like the notation in the with the expected return. So if I go back to let me go back to the slide. Variance in the you see this, and so this is how you do the variance in the with the probability notation. Anyway, think about it. Probability is always 1 over something, right? In our example, 1 over 60 is 1 over 60, right? If everything is 1 over 60, right? Then it will be just like the notation we you saw on the whiteboard. And you remember this is the notation for standard deviation, right? Greek character sigma, standard deviation of random variable x. And remember, variance is the squared term of the standard deviation, so sigma squared. Makes sense? But when you use sometimes standard deviation, right? Variance, right? The notation. When do you use Greek character? When do you use non-Greek character notation? Remember the difference between the sample and population. Population is the entire data set. Sample is a local data set. So Greek character notation is reserved for population. Okay, and the otherwise for sample you use just non-Greek character notation. Another thing. So for our random variable is apple's return, right? So what is the population of apple then? The population of, if you think about it, that is the entire data set for apple. If you think about it, Apple started out in 1981. I mean, they went public and they got listed in NASDAQ and started being traded in the stock market in 1981. So if you use, if you go back to day one of, Apple, 1981, right? Use the entire data set to calculate, mean and standard deviation. That's the population. But think about it. It's 40 years worth of data, 40 years, right? 480 data points, if you use monthly data, right? Monthly returns, 480 data points. Is it meaningful? I mean, is it useful? Or for that, is it meaningful? No. Why? Think about it. Over 40 years, how much did Apple grow? Do you think? In terms Apple in terms of return, of course. It's more than 10,000%, way more than 10,000%. And if you take average of such a wide range, you remember average is a neutral number. The mean of 400 data points, historical data. It's called also time series, right? The neutral number over 40 years is really, really useless. I mean, it tells nothing about what it's going to be next month. Understand? 40-year average tells very little about what's going to happen next month. It can tell something about what's going to happen in the next 20 years or next 40 years, but it cannot be a dependable guide for or inference point for the next month, right? So I've been telling you, if you want, anyway, the long run, the trend, right, deterministic trend will give you a meaningful inference point for long run, right? It cannot give you like last 5-year monthly return, right? Average of that cannot give you a meaningful guidance for tomorrow's return or next week's return, right? But at least it can give you a meaningful forecast for next month or the month after that, 2 months, into the future, 3 months into the future, right? And I told you, deterministic trend works in the long run, right? But what is the long run? You know, anything above 1 year is long run, right? Anything below 1 year is short run, right? So that means the reason we use 5-year data set, right? 5 years worth of data is to get a long run deterministic trend. But if the time horizon, I mean, if you're using like more than 10-year data set, right? 10-year, then it loses actual, it loses touch with the recent dynamics in the price, right? Think about it. If you use like 2 decades, data for 2 decades, right? Past 2 decades, right? Past 2 decades price actions, right? Past 2 decades price fluctuations, right? Has little relation with more recent, a couple of years price dynamics, right? So usually, the most common data range for time series or historical data range for the stock market is the past 5 years. They don't even go back to past 10 years, 5 years, because that would be more relevant to the most recent, more recent price movements, right? Okay, so with that in mind, so how does that? We already know that we can we can associate, certain, if you have a certain profit, right, target return, you can associate that with the probability, right? So that helps us. Well, okay, that's good. But can it nail anything with, what I'm saying is it can nail something with a probability. The range of probability can be more narrower, more closer, right? The range of probabilities. So if you are like, what's the probability of getting 15 to 16%? For that 1% return range, you can also nail it with probability. It's not a big deal. But then more than that, what's more important is, let's take a look at this example: asset allocation. So take a look first. So you, since now you know how to calculate the expected return, so you researched hundreds of stocks. You're doing some stock picking. And if you have $100,000 and you want to invest $100,000, you're not going to invest it blindly, right? You will do some research and you will pick some, possible, most likely possible winners, or most likely the likeliest candidates. So you researched, hundreds of stocks, and you came up with these 3 stocks, X, Y, and Z, and based on what? Based on their expected returns, right? 25%, 30%, 10%. Those are the expected returns, right? Now, so this, get the label, expected return on I. That I represents the individual stock. I means an individual asset. So for stock X, company X, the expected return would be expected return on X. This I will change, right? This will be permutated with these labels, right? That's how you do. I is just a like a representative, blank placeholder, right? So just like N, you're actually replacing N with specific time, right? So expected return on X, 25%, expected return on Y, 30%, expected return on Z, 10%. Now, so obviously with $100,000, you would allocate, most money into. You're not going to allocate all. Allocate. You're not going to put $100,000 into just one stock, right? Because why? It's basically, a common sense, right? Common wisdom. You don't put all your nest eggs into one basket, right? And obviously, between these 3 stocks, Y will be the most preferred because it's got the highest expected return, right? And then X will be the second, number 2, second preferred. Z will be number 3. But then think about it. So you might want to allocate the most of your funds into Y, and the second most into X, and the third into Z. But then the problem is, you're only looking at expected return, but you didn't look at the standard deviation. But look at the standard deviation. Standard deviation of X is 40%. Standard deviation of Y is 60%. Standard deviation of Z is 15%. And what is standard deviation? Standard deviation is the fluctuation, average deviation from the mean, average bandwidth of the fluctuation from mean. And the fluctuation from the mean, deviation from the mean is what? That's the risk. Isn't that right? Risk is, what did I say? Is the risk. Of course, in the bond, risk is, there's default risk, inflation risk, liquidity risk, maturity risk. Yeah. Yeah, of course, default means, you're not getting your money back. Of course, in stock, you don't call it default. I mean, because you didn't lend money to the company. You bought the stock of the company, meaning you voluntarily became a part owner of the company. So even if you get zero or even net return as the owner, that's only your fault, right? You can't tell anybody else. You can't hold anybody else accountable for that, but yourself, right? So it's not defaulting, but basically, risk is the probability of, including probability of loss, of course, losing all your money, right? Or not only getting a negative return, right? Losing all your money is getting a negative 100% return, right? Negative 100% return is losing all your money. That's the extreme bottoms, the extreme left side. I mean, you can't lose more than 100%. But to the right hand side, to the right tail, the potential gain can be more than 100%. It can be even 200, 300%. There's no limit to the potential gain, right? But anyway, so your risk is not only getting the negative return or getting 100% negative return or loss, complete loss, but also I've been telling you, risk is defined as the probability of deviating, right, from the predicted return, right, expected return. So even if the return is higher than the actual return is higher than the expected return, it's still part of the risk because it's the variability around the mean. Okay, makes sense. So risk is not only a downside. There's upside risk too. I mean, upside risk is not necessarily a risk because nobody will be unhappy when there's when your actual return is greater than the expected return. I mean, nobody will say, "Oh, I got too much return," right? Nobody will say that. And it's a pleasant surprise, isn't it? Right? It's a surprise. Risk is basically a surprise because that was something unexpected, right? What was expected was the mean, right? But either way, if it is greater than the mean or less than the mean, these are both are surprises, right? And then upside risk, it's called if you get higher than expected return, that's called upside risk. But if you get a higher return than expected, then this is a pleasant surprise, isn't it? Right? It's not something you would cry out or scream. You will scream with joy, if you get better expected return. But still, it's variation. In other words, it's the volatility, right? It's the volatility that's making it risky, right? And if you think about, of course, the meaning of volatility, to define it more correctly, volatility is not exactly the same thing as variance, right? But in the market, use the term volatility so frequently as if it is the variance. No, volatility is only the part of the variance that is associated with the market's movement. But anyway, we're going to come back to that more about the definition of volatility later. But look, if you look at the variance of the return, right? So far, I mean, we call it upside downside, because it's better than if it is better than the higher than the expected return, it's up. Lower than the expected return, it's bottom or lower. But then if you flip it and turn it on the side, put it horizontally, there's left and right. Right? Remember, if you put it horizontally, I mean, if you put it vertically, if you set it up, flip it vertically, then this would be upper side, this would be lower side. But if you put it horizontally, this is right hand side, and this is the left hand side, right hand side, left hand side. So think about it. It's like driving a used car. If you buy a used car, what would be your biggest concern? The biggest concern is, is the brake? Biggest concern is the brake going to work when I step on the brake? Is it going to stop the car when I want to stop the car? I mean, if the brake doesn't work, the worst, it's the worst kind of situation, right? You don't want that. Another thing is, are the wheels? It's a used car, so if you may end up buying a lemon, and then the wheels may be not well aligned, or wheels may wiggle, right? Especially if the front wheels wiggle. You got to do, the alignment is not. It's called alignment camber, or camber is the the angle of the angle it makes with the road surface, right? The surface. But I mean, alignment. If the alignment is wrong, or some things are holding the steering system right. If the steering system is faulty, then this is also a big problem, isn't it? Right? I mean, if the car is not a lemon, right? When you keep your hand steady, right, it should stay on course, right? But if the steering system is faulty, then even if you keep your hand steady, the car may careen to the right or careen to the left. And this is a very dangerous situation. So it doesn't, think about it. Careening to the right is getting, a higher return than the expected mean. Careening to the left is, getting lower. Either way, higher return or lower return than the expected return, still they are both risk, right? Hence, that's why it's called risk. And they specifically, usually, you're getting something above the mean, that's called upside risk. You're getting something below mean, it's called downside risk. And they would focus more on the downside risk than the upside risk. Now, but we spent a lot of time, but here. So let's think about it. If you consider the risk here, X has 40% risk, Y 60%, Z 15%. So this is pretty much, this goes pretty much, in concert, hand in hand with the old, conventional wisdom. Why? The conventional wisdom is what? The higher the risk, the higher return. The higher the return, right? The higher the risk, the higher the return. Lower the risk, the lower the return. Right? Makes sense? Then, if you consider the standard deviation, decision number 1, decision number 2, decision number 3, right? So they are in conflict. These two criteria, decision criteria, are in conflict with each other. Right? This is a mind-boggling situation. I mean, if you can go with one criteria, go by only one criterion, it would be wonderful. But when you have to go by two criteria and they are in conflict with each other, then this is a mind-boggling situation. Right? So what do? Well, then you will have to come up with some smart solution with that. And the smart solution is, return risk ratio or mean variance ratio, or mean variance ratio. What is mean variance ratio? Mean variance is also called, return risk ratio. This is mean, right? Expected return is mean. Standard deviation is, you might say, oh, so should it be called mean standard deviation ratio? Yeah, you can call it mean standard deviation ratio as well. But you remember standard deviation and variance are like twins, right? They are like twins. So you can call it mean variance ratio as well. Now the idea is, why do you take this ratio? In this, remember, when we did, a lot of things, a lot of things in the world uses better to cost ratio or output to input ratio to measure what? To be efficient, right? If the output is high for input, the efficiency is high, and everyone prefers higher efficiency than lower efficiency. Makes sense? So think about it. And I've been telling you, think about it. Mean is the output. The expected return is the output. That's the benefit, right? And the risk is the input. Isn't it right? Risk is the cost. I mean, to get output, you must run this risk. To get this output, you must invest, pay this cost. Make sense? So then the higher this ratio, the better it is. Make sense? And I've been telling you all the time, as an example, typical example of mean variance ratio or return risk ratio or output to input ratio. What did I give you? Gas mileage. Didn't I give you gas mileage? Right? Gas mileage is a typical example of output to input ratio, and everybody likes. Gas mileage is also called fuel economy, and everybody likes higher fuel economy than low fuel economy. This isn't it right? Any rational person. And if you prefer low gas mileage, you're not a rational person. Why would you want a gas guzzler, that runs, 0.1 mile or 10 gallons? By burning 10 gallons of gas, you just cover 1 mile or 0.1 mile. That is just, even a tank, M1 Abrams tank, will have a better gas mileage than, that. Right? Makes sense? But so the idea is, if you take the gas mileage on, simply like mileage on the stocks, right? The higher the number, and you do this has the highest, right? This is the highest, right? This is the second best. This is the third, right? Okay? So then what? You will allocate the most of your funds into the number 1 stock, and second most into number 2 stock, third into number 3 stock, and your expected return on the portfolio consists of these 3 stocks. And your return on the portfolio will be the maximum. I would say it will be exactly the maximum, but it will be better than any other allocation, right? Of course, you can reach the maximum return by knowing exactly, by getting the exact optimal allocation weight, right? Optimal weights. By finding optimal weight, then you can reach the maximum portfolio return. That is the top reserve for 300 investment analysis. And then interesting thing is in the U.S. In the U.S. our gas mileage is miles per gallon, right? To calculate that mileage, what you do if your car has 20 gallons, right? Run out of gas. And if you covered 600 miles on a full tank of gas, right? 600 miles. I mean, that's a very crude way, but it's a very honest way. 600 miles divided by 20 gallons, so that's 30 miles per gallon, right? So miles per gallon is in a lot of countries use inverse gas. What's an inverse gas mileage? Inverse gas mileage is like liter per kilometer, right? Like in the U.S., gallon per mile. That's unthinkable in the U.S., but in most other countries they use liters per kilometer. So if you use inverse gas mileage, right? It's not output to input ratio. It's the reciprocal, right? It's the input to output. So that means the lower the number, the better it is. Lower the number, the better it is. So think about it. To run 100 kilometers, so it's like per 100 kilometers. So 100 kilometers per liter to use, right? The lower the number, the better it is. And this is used by most countries, right? And then also for mean variance ratio, they have also the reciprocal of mean variance ratio. So this is a right? Right? Reciprocal, and that's coefficient of variation. If we use coefficient of variation, the lower the number, the better it is. Still, you come to the same result. In terms of ranking, Z is your number 1 stock, X is your number 2 stock, Y is your number 3 stock. And then the weight allocation, I did it mechanically. This weight allocation, weight distribution was done mechanically. It doesn't have to be done exactly this way, but you can use some arbitrary method. But see, the most weight is allocated into our number 1 stock. Second most weight is allocated into our Z. A third is allocated into Y, and sum of all these weights is 1, right? Of course, they cannot exceed 100%, right? All right. So that's it for today. We'll discuss further about this in our next class. Okay, thanks for watching. And
all right. I mean, during this video, there was a problem with the audio. I admit, and I'm sorry about that. I don't know what happened while something was not quite right when I was recording it. So there was some part of it was gobbled up, but I guess you get the idea, right? Now, one of the very crucial goal or purpose of mean and standard deviation is this. In other words, mean variance ratio or return risk ratio, right? And the return risk ratio is basically gas mileage. I mean, gas mileage is a good example of mean variance ratio, or output to input ratio. Now think about it. When we measure the output against the input, right? That is a indisputable and undeniable measure of efficiency. Isn't that right? The greater the output for the given input, right? The higher the efficiency, right? And you might say, oh, isn't that the productivity? I mean, output to input, output over input, isn't that the productivity? Yes. However, when we say efficiency, we want the highest ratio. I mean, productivity means, it could be output to input ratio can be 1, 1.25, 1.5, 1.75, or 1.2, 2. There's a wide range of numbers for this ratio, but the highest one among all the possible output to input ratios, the highest one is the most efficient one, right? Does that make sense? So this expression, expected return over standard deviation, right? That's clearly, output to input ratio, right? So obviously, if the ratio is the highest, right? Among these, the highest is this one. Second highest is this one. Lowest is this one. So you can rank these stocks by output to input ratio, or mean variance ratio, or mean standard deviation, or return risk ratio. So rank number 1, number 2, number 3. And what about this? This means coefficient of variation, and the textbook is talking about the coefficient of variation. Coefficient of variation is the reciprocal of this. So reciprocal, raised to -1. So it is basically a standard deviation over mean return. And as an example, I gave you in the video the inverse gas mileage. And in a lot of countries, they use inverse gas mileage. It's not miles per gallon, but most other countries use liter per 100 kilometers. Liter per how many liters had to be used to run 100 kilometers. And this makes sense in those countries because most other countries are not oil producing countries. US is an oil producer. So basically, even if US doesn't import oil from Saudi Arabia, US can pump up oil. Of course, and the shale oil reserve that was actually discovered. It was discovered a long time ago, but it was brought to light. It was brought to spotlight back in Obama administration, during the Obama administration, because it was the time when President Obama said, U.S. shale oil, they will last, for the next 200 years, at least next 200 years. Even if you pump up, every, and also shale is basically, the shore part of the shoreline is probably like 2-mile stretch, shallow area of the sea, right, from the beach, right, from the coastline, right. But even inland, remember Texas, a lot of oil rigs. You might say, oh, only Texas and Oklahoma. Not only there, but Pennsylvania has oil rigs. But, they have to use, a technique called, fracking, which is environmentally hazardous. So it's very, they make it very difficult to use fracking. Anyway, but, it's not cost effective either, right? Fracking is not that cost efficient, so they don't do it. But in the countries where oil is abundant, they are not too conscious of conserving natural resources. However, in the countries where they don't have any oil, very conscious of conserving
or natural resources, or saving gas, right? So that's why they use inverse gas mileage, right? So this is coefficient of variation. Coefficient of variation is like inverse gas mileage. Okay. So if you wonder how I got this, I mean how I got these weights, I didn't explain it here. And if you go back to also, if you want to know more about degrees of freedom, I've updated uh, this page with links to degrees of freedom. Please look it up. And how did I get that? So it's like this. I mean, so we have draw. We have three stocks, ranked number 3, number 2, number 1, right? If you sum all of these,
Like this?
yeah. Hello, was someone trying to say something? Uh, this sum of all of these numbers is 6. Then I use this for the largest weight. Right? And think about it. These numbers are exactly 50%, right? 50%. And 2/6 is this, 1/3, 33.33, and 1/3 is this. So this is, rather arbitrary, but kind of mechanical, right? I mean, it's not like, oh, so what should be the percentage in stock 1? I mean, the first, rank, um, the stock that is ranked first. What should be, that randomness is eliminated. Of course, you can put 75% in this, right? 15% in this, 10% in this. But because it's there's so much randomness, and you might wonder, isn't 75% too much? And besides, your concern is this is safe. This stock is safe, but putting too much weight into this would result in very low return, low portfolio return, right? So that's why, right? And of course, sum of all these weights is 1, right? So it's kind of nice, but anyway, so that was, how I came up with, this way. Okay, these weight distributions. Okay, any questions? Any questions so far? Any questions? Any questions? I'll take it as no. I guess Malaysia was trying to say something. Microphone, but I'll take it as no. All right. So class is dismissed. Okay, please go in peace, and I will see you guys all back tomorrow at 6 p.m. All right. All right. Have a great evening, everyone. You're welcome, Zainab. Have a great evening.
Malaysia, do you have something to say, Malaysia? Malaysia, your microphone is on. Have something to say?
Thank you, Professor.
All right, you're welcome, Brendan. Take care. Good night. Okay. Good night. See you tomorrow. Good night, Coral. I will see you tomorrow. Okay. All right. Stop recording.